All right, let's get started, everybody. Let me get the lights adjusted a little bit. All right, everybody, welcome to Steel Design. I trust everybody had a good break, and that it was, relatively relaxing one. I think it felt like this break was a little longer than it normally is, but I know my daughter was definitely ready to get back to school today because she was supposed to be back last week, and then they kept canceling school because of all the weather. So yeah. All right, so a couple just quick housekeeping items. Y'all know I'm pretty much around whenever you need for questions and whatnot. But I will say I have dedicated office hours on Monday, Wednesday, Friday from 1 to 3. I say Tuesday, Thursday by appointment because there might be some days that I'm not in earlier or some days I'm just sort of handling a lot of the associate dean stuff I deal with and whatnot. But I am generally around, I think, as you all are aware. I did put on the attendance questionnaire just some info about the manual. I'll get into that here in a bit. We won't desperately need the manual in class until week 3, and so what I mean by that is starting in week 3, we are going to use it pretty much every day in class. But for the first couple of weeks, I've sort of designed the homeworks where if you're still waiting on it to come in the mail and whatnot, especially given our inclement weather and whatnot, you'll be fine. There is one slight exception to that, and that's homework 1.2, because homework 1.2 is sort of a force you to open the manual and look some stuff up type assignment. But if you're still waiting on the manual to come in and whatnot, I won't count that homework late. So I just throw that out there. Okay, let's go ahead and jump right into it and talk about the class. So what I'm going to do today is just go through the operation, go through some ways that the class is going to operate, talk a little bit about just steel design in general, and then we'll get rocking and rolling. Okay, so let's talk about the grade in the class. So I've elected not to do a design project in here, not because I think design projects are bad ideas and whatnot, but just we have a lot to talk about in here, and sometimes a project can take away from that. I am going to do some, I'll call it project-related material near the end of the semester, so I'll sort of take a lot of what we talk about throughout the semester and sort of tie it together with real-world applications near the end. But for the most part, this class is going to operate just like my class operated last semester with the homework assignments and whatnot. I'll pull up the schedule here in a bit. But the regular homework assignment schedule that we did in instructional analysis is pretty much going to be the same pattern as is here. There are 3 exams in the class. The exams are not intended to be comprehensive, okay? And if there's any one class where the exams truly are modular, it's probably this class. So, for example, our first exam is going to be on tension members, and then our next exam 2, is going to be on connections. And they truly are different topics, and they truly do, they truly are pretty separate. Now, again, just like with structural analysis, some of this material has a way of bleeding over from one exam to another, but I would say in this class, more than any, that effect is probably pretty minimal, okay? In terms of the required materials for the class, there is no required textbook, and I make up all the homeworks and lecture notes and exams myself, so you don't have to buy a book, but you do need to acquire the manual, okay? This is what the manual looks like, and so one reason I throw the image here on the screen is that some of you might have friends that work in, let's say, a design firm, friends that have had this class before. Maybe you have a sibling and whatnot that has a copy of the manual and you want to borrow the manual. That's totally fine, okay? The only 2 things that really, well, I guess 3 things that you need to be aware of. One, you need a physical copy of the manual. A digital one isn't really going to work well on exams and whatnot. you do need your own manual, okay? And so by that, if while you're waiting on your manual to come in, like let's say it's, you know, the UPS or whatnot is delayed and you need to do a homework assignment, if you want to borrow one from a friend, that's fine, but you do need your own one from the exam. But third, it's got to be a gold manual, okay? The manuals, they change color as each edition comes out. So this is the 16th edition. So for example, the last edition was sort of a, like a turquoise color, a little lighter than your hooded sweatshirt, but kind of like that. So if you have like a blue manual like that, that's an older edition and it's not going to work. You do need a gold one. But as long as everybody has a physical gold manual that they can rely on, I really don't care how you get it, okay? Please do not purchase one, though, without using that coupon code. Please don't do that, okay? Because it is really expensive. It's like $400 without the code or $125 with it. So, you know, there. If you can find it cheaper on eBay or Amazon, my hat's off to you, but I just don't think you will, okay? It's just that competitive of a price. Okay, I do want to pull up, before I get into the process here, I do want to pull up a couple things on the syllabus, and I want to pull up some things on Blackboard. Okay, so let's see what's worth mentioning here. Okay, so I've already talked about the grade distribution for the class, so I don't really need to get into that. A lot of the stuff that you see here on technology and whatnot is all the same as it was in structural analysis, and we're really not going to use any software packages in here beyond Microsoft Office. The one package that we will use a little bit in here is Excel, but other than that, nothing in here that's fairly demanding. I do want to pull up the class schedule, so let me see. I don't know if everybody can read that. Can you read that? Okay. So a little bit about the day-to-day. So first off, so let's talk about exams. So our first exam is going to be on Wednesday, February 12th. I don't know if you all have looked at the academic calendar this semester, but if you remember last semester we had an October break. Well, we have a February break now. So my idea is that the first exam, it does sort of work out really nicely where we can take that exam right before break so you all don't have any work after that. You can sort of take off of this class for a few days. Let's see, for exam 2, it doesn't really work out as nicely to where we have, where we can do the exam right before break. Connections just isn't that long of a topic. So what we're going to do is we're going to, for the second exam, we're going to review on Friday, we'll have the exam on Monday, and then what we're going to do is we're going to come back on Wednesday, we're going to have one lecture of column theory. I'll give you one assignment on that, which is just an Excel-based assignment. You'll turn that assignment in the Friday before spring break, but we don't meet that Friday before spring break, assuming, you know, weather cooperates and whatnot. And so you turn that in, and you get spring break with no outstanding work. Like, I want break to be a break. Okay? Sound good? All right. So let's see. I should mention, again, the homework schedule is the same, pretty much the same as it was last semester. So I'll give you a homework assignment pretty much at the end of every lecture that's due the following lecture. But you all know, as well as I do, that the homework assignments are short, like they're pretty short. And if you're curious on length, I would say that the homeworks are probably just a tad shorter in here than they are in structures, okay? The main reason why is that, if you recall, structural analysis requires a lot of figures, a lot of images, a lot of sketches. Steel doesn't really, it's not as demanding in that regards in terms of writing out sketches and figures and free body diagrams. You don't really need to do that. You're just sort of doing calculations. Maybe the problems themselves are a tad longer, but because they don't require all the sketches, you'll actually be able to do them pretty quickly. So I would say that on average, these assignments are a little shorter. Okay. In terms of turning them in, again, it works the same way as it did last semester. So if you want, you can do the assignment on paper, scan it, upload the scanned PDF, or if you want to do it on your tablet and then upload the electronic documents, you can do that too. That's fine. As long as it's legible and professional, I don't care. which method that you use to do the assignment. Okay. The final is on May the 9th. We sort of drew the short straw in that we got the final on Friday, which sucks because then I got to grade it, and I don't have much time to grade it, but that is what it is. So our finals Friday of finals week at 8 o'clock in the morning. The one thing that I will mention this semester is that I have changed things up a little bit in the class from previous offerings where we went from 14 weeks to 15 weeks. And so what I did is I sort of separated the wheat from the chaff in terms of some of the topics earlier in the semester because I wanted to open up some stuff near the end of the semester on building applications. So a lot of what we're going to be doing this semester is very element-based design, like how to design a beam, how to design a column. And I want to sort of talk a little bit about, okay, well that's great, but how do we tackle a whole building? Because that's ultimately what you're going to need to be able to do is not just design individual elements, but whole systems. So I'll touch on how that works. And really the big challenge between element-based design and looking at the whole system are the loads. So I should mention that these homework schedules near the end might change a little bit, mainly to give you more time, but I won't start unduly adding workload to you. I believe most of you have had me for enough classes that you know I'm good about that. All right. Any questions? Okay. Let me pull up Blackboard. So a couple things about Blackboard. One thing that's worth mentioning, so Marshall sort of changed its policy on Microsoft Teams. What it used to do is it would automatically generate a Teams channel for every class. Now they're sort of letting the professors do it if they want, because I think they found a lot of professors just weren't using it. And I'll be blunt, I don't know that I was really using Teams all that much, but what I was using was the OneNote, okay? So what I did is I put a link here in Blackboard for the OneNote for the class. So I'll do all the whiteboard calculations here and there so that you all should be able to access it. Just like it was in last semester, it'll be in the content library there. And so if you have trouble accessing this, let me know. This is my first time sort of setting it up this way, so I just wanted to throw that out there. I am recording the lecture, both the screen and the audio, and I'm going to post that to a YouTube playlist, which is linked right here. So all the recorded lectures will be right there. I've got the syllabus posted right here. The other thing that's worth mentioning is that if you go down here into lecture notes, I've got everything up through the first exam posted. Okay. So I'm going to do my best this semester to try and post everything en masse and just sort of, here it is. So everything up through the first exam is right here. I'll go ahead and point this out now, and I'll probably mention it a little later. There is this thing called AISC errata, okay? And what that is material related to the manual itself. And there are two things in here which are really important. The first, or beyond the coupon code, so the coupon code's in here. But beyond that, the first is what's called the shape database. And so we'll talk about this a little bit later. But if you open the early part of the manual, there are all these dimensions and details for all the rolled shapes that we use. And there's a big old Excel spreadsheet that has all that info there. And then the other thing is the actual code and specification document. And we're going to spend a lot of time this semester reviewing that. But the code and the specifications in the back part of the manual, it's in this rear part back here. And there's a PDF of that as well. So I just throw that out there as stuff that's there that you can use and download at your leisure. Okay. Any questions? Okay. All right. So let's get into it. All right. So I'm going to talk just a little bit about what it is that we're here to do, why we're in this class, what we're hoping to achieve. And so I want to talk about the structural design process. I think that we all have, hopefully, a pretty good understanding of what the structural analysis process is. Okay, so maybe let's talk about that a little bit. So the idea behind structural analysis is I give you details about a system. Okay, so what do I mean by details about a system? Well, I need to tell you about the geometry of that system. You know, if let's say it's a truss. Okay, what are the dimensions of the truss? Where are the members? you know, what are the support conditions, all that. I need to tell you the constitutive properties of those truss members, what materials they're made out of, how big around they are, and so on and so forth. And I need to tell you about the loads that we apply to them, if there's a joint load here or point load there or whatnot. And then what you do is you take that data and then you perform an analysis and you get results from that analysis. And what are the results? You get support reactions, you get deformations, you get, if it was a truss, let's say we have whether this member's in compression, this member's in tension, this is a zero force member, so on and so forth, right? And I think hopefully at this point everybody kind of understands that, right? Okay, well what are you supposed to do with that? Okay, I have a truss member that has 320 kips in tension. All right, now what, you know, okay? And that's where the structural design process comes into play, okay? One of the ways I like to start is maybe we should have had this slide last semester. I do think it's a little bit more appropriate to talk about this now, but what is structural engineering? Like, we all know what, hopefully, we all have a general idea of what civil engineering is and whatnot, but what is structural engineering? My definition for that is it's the science and really kind of the art of designing structures so that they can safely resist the forces that they're subjected to. That's pretty much it. Structural engineers, they tend to work on two classes of structures, buildings and bridges. A lot of what we're going to do in this class is going to be geared towards building design. However, the element level design for buildings and bridges really isn't all that much different. In other words, a steel beam doesn't really care where it is. It's going to behave the way a steel beam is going to behave, if that makes any sense. So we're going to learn how to design a beam, and the only thing that changes between buildings and bridges are the loads and the demands and whatnot. Really what we're going to be focused on the entire semester are these two boxes, okay? And I would say that this box over here on the left is primarily what we talked about last semester, okay? I have loads and resistance. If we were in an economics class, we might be talking about demand and supply, okay, if we want to think of it like that. But essentially what we're talking about is we have a system that is subjected to some sort of load, and that load could come from its self-weight, it can come from environmental factors, it can come from its use, and what have you. And then on the other end we have resistance, how strong the system is, how much load can the system withstand before it fails, okay? And as long as the resistance is greater than or equal to the loads, the system is safe, okay? That is pretty much the crux of our entire semester, is this comparison of loads and resistances, okay? And that's what we're going to be focusing on quite a bit in here, but we'll take it one step at a time. Now, I give this example to, when I do tours of the building and whatnot, I'll have parents and high school kids interested in engineering. I give this example, and I'm going to give it to you same as I give it to them. So let's say that, and I'm going to use bridges because I can't help it, but let's say I'm a bridge engineer and I'm designing a bridge in the Barbersville area right down the road. And I know that when that bridge is complete, that my grandma's going to drive over that bridge every day, okay? And I'm not going to let anything happen to grandma, okay? So I'm going to design that bridge to be super stout. I'm talking tons of reinforcement, massively deep beams, so that nothing will affect that design. It can hold up any load that it's subjected to, okay? What's the problem with my approach? It's too much money. That's exactly right. It's too expensive, okay? There's an old joke among engineers, among bridge engineers, that anybody can design a bridge, but it takes a bridge engineer to barely design a bridge, okay? And it's a tongue-in-cheek way of making a very critical point, is that on one end, engineers cannot design systems that compromise the safety, health, and welfare of the public. It's our primary concern, okay? But beyond that, we have to design systems that are efficient and economical, okay? And that's really where the challenge of structural engineering comes into play. We're going to talk a lot in this class, especially when we get into design, as to what it means to provide an economical solution. We're going to have a really simple way of determining that, and our way of determining that is going to be based on weight, okay? In other words, if I'm designing a beam, let's say we're designing a beam, and you have an answer, and you have an answer, Okay, I'm going to look at your two answers, and if your answer is lighter, then yours is the most economical. Okay, and the reason for that is if we're paying for steel on a per pound basis, the lighter design is going to be less steel. Less steel is going to be less money, right? So that's going to be our metric. That's not always the metric. There's some more nuance to that, which we might talk about, throughout the semester. But generally, that's going to be our North Star in terms of our designs, is that whatever design is the lightest is going to be the most economical. I'll give you a slight caveat that you'll understand what I mean. So let's say I was designing the beams in this building, okay? I could design every single beam according to the lightest weight possible, and what I might end up with is a Rubik's Cube of a frame with 500 different beams. That might be really difficult to put together. It might be easier to take those 500 shapes and whittle them down into half a dozen or so that just get repeated over and over again around the building. Now, does that mean that there's going to be a few beams in the building that are over-designed? Yeah, it is, okay? But is that going to mean a faster and more optimal construction process? Yes, okay? Not only is the frame going to affect the cost, but the construction as well, okay? And so there might be systems that you use that might not make sense from a weight standpoint, but it might save you labor. It might save you time, okay? So I just throw that out there as just sort of a nugget to think about. Okay. I am going to throw some terminology out at you today, and I'm going to use this terminology throughout the semester, but one of the terms I wanted to put in the back of your head right now is what's called a limit state, okay? So the reason I mention that is because we're going to be using a design philosophy in order to select members, and the name of that philosophy is LRFD, Load and Resistance Factor Design. But really, LRFD is just a limit state design based process. And so what is a limit state? A limit state is a condition that we as engineers define, and we basically say if the structure goes beyond that condition, or if the element goes beyond that condition, then the structure is no longer fulfilling its design criteria. So a good example of that might be, okay, here's a beam, okay? The beam has some load on it, okay? So a limit state might be strength, okay? So we'll calculate how much load the beam can be subjected to before it fails, and we call that its strength resistance or whatnot. And if the load exceeds that, then we say we violated that limit state, because if we exceed that, the beam will fall down and kill people. Okay, so that condition, that idea of strength under bending, we would call that a limit state, and that's not the only limit state that we deal with. Strength limit states are a very common class of limit states that we deal with. So strength limit states, which is what we're going to spend a lot of our semester on, is going to be, strength and axial load. So for example, the strength of a tension member, the strength of a compression member, the strength under moment, the strength under shear. And that might be an interesting discussion point right now, is that why would tension members and compression members have different limit states? Well, think about a truss, right? So trusses have tension members and compression members, but why would we design them differently? Well, compression members like to do this thing called buckling, and tension members don't, okay? So the mechanics are different, and so because of that, we have to handle that a little bit differently. Things under bending don't behave the same as they do under shear and whatnot. All right, so strength limit state is one class of limit states. Another is a service limit state. And a service limit state is a little different. So service limit states aren't really intended to govern against the structure falling down and killing people. A service limit state is more about a structure's day-to-day use. It's normal wear and tear, normal operations. I'll give you an example of a service limit state. I'm going to use beams as well, okay? So there's going to be beams up here that are supporting the floor, okay? That are supporting the floor from upstairs. And I can think of two limit states, at least, that those beams are going to have to withstand, or going to have to meet. One of them is strength, right? The beam has to be strong enough so that the load doesn't fall down and kill people. but another is a limit on deflection, okay? And so one limit state that we'll have to consider is a live load deflection limit of probably L over 360. Now, L over 360, what we would do is we would take the length of the beam, we would divide it by 360, get a little number, and we would say the beam cannot deflect more than that. Now, we all know how to calculate beam deflections. We did that all last semester. But what, from a design standpoint, we would be saying the beam can't deflect that much. Now, why? Are we saying that if the beam deflects this more than this much, it's going to fall down and kill people? No. Has nothing to do with it, okay? That L over 360 comes from day-to-day intended use. So I'll tell you where that limit comes from. How many of you have ever been in a house that has a plastered roof? Like the roof has like a plastered roof or like a drywall-based roof and whatnot. So if you start exceeding L over 360, the plaster will start to crack. Has nothing to do with the building falling down and killing people, but the building's not serving its intended function if it deflects that much. And while that limit came from plastered roofs, it does tend to work pretty well for framing of structural systems in general, so we use it pretty precipitously, okay? And so that's one service limit state. There's others about, fastener slip, about, motion and vibration, human discomfort. Some of that stuff we'll talk about a little later, but I just want to throw that out there. We won't talk about some of this like in great detail, but I do want to throw this out there, is that there are structural objectives that you're going to have to deal with, particularly in the real world when you're designing systems. This won't really affect your calculations, but it is sort of a real world consideration that you need to think about. So, for example, aesthetics. If we're talking about building design, we typically work for the architect or the A&E firm. So the way I like to describe it is if, let's say, Geico Insurance wants a new corporate headquarters, okay? So Geico will contact, let's say, a land developer or an architect to come up with the general layout of the building, like what the building's going to look like, what's ingress and egress going to look like, how many conference rooms there are, how many offices there are, and so on and so forth. And then it is the structural engineer's responsibility to then take that building and make sure it doesn't fall down and kill people, right? Now, in that world, you're really sort of working for the architect. I mean, to put it like this, the Gecko doesn't really care if the building's made out of steel, concrete, popsicle sticks. They don't care, right? They just want a building that works. But you need to work with the architect to develop a system that makes sense. And I'll give you a real example of that here in a bit. On top of that, you do need to develop a system that is easy to construct and erect. There are plenty of memes out there of engineers or connections that have been designed by engineers that are pretty much impossible to put together in the field. So you want to make sure that the details that you're putting forth actually make sense from a fabrication and erection standpoint. One thing that's also pretty interesting is that sometimes the loads that you see during construction are actually worse than the loads during the final finish stage. Actually, the highest stresses and the highest design considerations are actually during construction. And so does the structural system possess enough capacity to even survive the construction process? And then obviously, economy as well. And I throw this out here just as this is very high level, but it's just something for you to think about, that whenever you're beginning a structural engineering project, there is sort of an inverse relationship between your ability to influence the cost of a project over time versus the cost of those changes should you decide to make them. Like, for example, if you're in the beginning phases of a project, the conceptual planning doesn't really cost that much money. But those decisions that you make have a very significant impact of the cost of the project over time. But on the flip side, right, once the project started and you're erecting it and fabricating it, but you really don't have much influence over the cost. But if you wanted to change the framing after you're on the ground floor, after you're putting the roof on, that's going to be some money. That's going to be a change order. So you just kind of need to keep that stuff in your head. Okay. Like I said, this class is going to be focused on building design, and I want to talk about the types of elements that we're looking at, the types of loads that we're going to be subjected to. I kind of wanted to start out, hopefully, with something that's a little bit familiar. I'm curious if anybody knows what this is. Is it the business building?
Yeah, the new one that was just constructed.
That's a good guess. That's not right. But I said it was a good guess. Anybody know what this is a picture of? If it's not the business building. It's this building. There we go. This is this building. I'll give you a hint. Does anybody see this back here? This right here?
Yeah.
That's the strong wall in the lab back there. This is this building. So what you're seeing here is the frame on that far end of the building. Okay? So this right here, this stair set right here, this is the walkway between the two engineering buildings. So if this picture were to go on this way, you would see the old engineering building. Okay? So these are some pictures that were taken of the building as it was being constructed. So a couple of things that are worth mentioning is that it does look maybe a little on the challenging side. It's a little intricate. And don't get me wrong, from a load calculation standpoint and whatnot, there's a lot going on here. But when you sort of break this structure down into its constitutive components, there are really only 4 types of components that we need to consider for structural design. Okay? And what are those 4 components? Well, I see some beams, right? Which we're going to talk about later this semester. I see some columns, which we're going to see later this semester. So beams and columns, and that's the bulk of the frame. Ironically, we talk about beams and columns last in this class, not because they're the least important. I'd argue they're actually the most important. But the math for designing beams and columns are pretty intricate, and I don't like starting with that because I think we need to start with topics that make using this straightforward and doable. Okay? So we're actually going to start with tension members. And do I see some tension members in this building? Yes, I do. Does anybody see these right here? Those are braces, okay, that are keeping the building upright under lateral load. Okay? So we have beams, columns, braces, and our 4th most important element, connections. Okay? The elements that connect the pieces together. And whether we're talking about this part of the building or this is sort of zoomed in where you can see these braces a little bit, you can see these all over the place. One of the things I do like to point out about the bracing system, so if you look here, so this is, you know, a view of the building, and you can see these sort of like inverted V-looking braces right here. One of the things that's worth mentioning is that you actually don't put lateral bracing everywhere in a building. You just put it where you need, okay? So to sort of make the point, let me give you a different example. Let's say that you're in a car with your friend. You're in the passenger seat, okay? Your friend is a horrible driver, okay? They are driving 55 miles an hour down the road, probably speeding. They see something in the road, they hit the brakes. What's the first thing that you hit?
Your seatbelt.
She knew what she said. She said seat belt. Right? Yeah. Sorry, I can't help it. That's funny. No, but here's my point. In a vehicle, we do not design an entire system to restrain you. We don't design the entire car to hold you back under a lateral event. We install a system in that car called a seat belt, and it is just that seat belt that's meant to hold you back. Okay? So the idea is that if this building is subjected to wind or earthquakes or something like that, we don't design the whole building to keep you up. We just install bracing in key locations that are meant to hold the building up under either wind or earthquakes. Those are our 2 big lateral effects and whatnot. And if we look at this system, it does sort of behave like a truss. And so we'll actually have a little problem on that a little bit later this month. This is a bigger view of this frame, and again, I think the point I wanted to make with this image, or even with this image inside the building, is that even as the building erection gets more intricate and complicated, it's still just a bunch of beams, columns, connections, and braces and whatnot. So if we look here, this is sort of a three-dimensional ISO image of a building, and we can see this. I should mention also the floor system as well, although for the floor system, at least for structural steel framing, the floor system's actually a pretty easy component to design because it's usually a lookup. Really where the challenge comes in is the beams themselves. And so I say we have main and secondary beams. You will probably use the term beams and girders, and I'll show you an image of that here in a bit. But yeah, like I said, beams, columns, braces, and connections, that's pretty much the be-all, end-all of a framing system. So if we look at, let's look at how buildings would transfer what we call gravity loads. So we're going to talk about two different groups of loads in structural engineering, and those groups of loads are going to be gravity loads and lateral loads. So gravity loads are, like they sound, ones that act in the direction of gravity. So the three most common are going to be dead loads. Dead loads would be like the self-weight of the structure, like if we're talking about this building, the steel, the concrete, the drop ceiling, all that stuff. The live load is going to be the occupancy, what the building is used for. So, like, for example, if we're talking about this building, we might apply a live load of, 50 pounds per square foot to account for us, the desks, and all that. Whereas maybe in a library, we might use 150 pounds per square foot. Why are we using 150 pounds per square foot in the library versus 50 pounds per square foot in this classroom? The books, because the library is filled with all the books that college students don't read. So, that was a joke, not a funny one. But in all seriousness, the books represent a different occupancy for the building. So if you think about it from a structural design perspective, the floor system in a library has got to be much more stout than the floor system in this building, right? Because the loads are different, right? The third primary source of gravity loads are going to be those that are related to the environment, and the most common one that we need to think about is snow. Obviously, right? And so dead, live, and snow are the primary load components. And so the idea, like, where does the load go? Okay, so we have a floor load on a building. So what happens is the slab will take that load and it will distribute that to the beams. And so the beams, we might treat those beams as simply supported beams with uniformly distributed loads, something we all know how to do from last semester. And we might get reactions from those beams. And so this girder sees a reaction here, a reaction here, a reaction here from all those beams that frame into it. Then those go to the columns. Columns go to the foundation. Foundation goes to the ground, right? So that process, what I'm doing is what I'm calling a load takedown. So the idea is taking the load from us down to the ground and whatnot. And we'll get into more detail about how we do this a bit later. But the long and short of it is this is just a tributary area problem. Remember how we did that in the project last semester? Same idea. Remember how I said that one of the things that we have to work around is architectural constraints? So let's take a look at this image here on the top right, okay? So this image here on the top right would be if I took a samurai sword or lightsaber through the floor system. And so what do I see here? I see this. This is what? The drop ceiling. This is the drop ceiling right here. And so I see, some duct work. I see the floor beam. And then I see the, the deck pan and the concrete, right? So I have to provide a floor beam that's strong enough to support all these loads. So an architectural constraint, I have to fit that floor beam in here. It can't be deeper, right? Because the architect said this is how much room you've got, okay? So this is an architectural constraint that we would need to operate under for the purposes of design, okay? And so I just throw here some images here just to give you an idea of what the anatomy of a typical floor system would look like. So we would have the beams going into the girders going into the columns going into the ground. We can see these connections that connect the beams and columns and whatnot. The floor system itself is usually a metal deck pan that's filled with concrete, which is actually what we used. Here you can see in our building we did the same thing. So here you can see the deck pan that they would then fill with concrete and whatnot. It's a very, very common floor system. Another floor system is to use what are called open web joists. How many of you have ever been to this? There's this store called Walmart. Have you been to Walmart? And you look up, what do you see? You see those? Those are open web joists. So they seem really complicated. Really, you just pick them out of a catalog. They're a lot easier than you would think. And here are some common floor systems. So again, this is a composite floor system. This is the deck pan, and this is something that you would see in a warehouse or a Walmart type store and whatnot. Now, the way lateral loads work is, so again, the idea with a lateral load is there's two really primary lateral loads that we need to consider in building applications, and that is wind and earthquakes. Okay. Now, we don't really need to deal with earthquakes so much around this area, although we did have an earthquake not too long ago, very small one in the area. So get like two googly eyes, stick them to the wall, boom, earthquake detection kit. Science. But as a joke, not a funny one. But again, as I mentioned, when we have a lateral load to a system, we don't design the entire building to withstand the lateral load. We only design certain pieces of the building. So for example, if I had a building and I had wind going to the building, what I would probably have is just a series of brace frames or whatnot that are meant to keep the building upright. I should mention that lateral earth pressure is also a lateral load, but I'm sort of not equating that in the same category as wind and earthquakes and whatnot. A couple of the common types of ways that we resist against lateral load, the two most common are what are called brace frames and moment frames. So to give you a CE 312 equivalent, a brace frame is basically a truss. We literally stick a truss inside the building at key locations, okay? And talking about architecture, you know, there are limits as to where we can place that. You know, the architect doesn't want a big old brace right here in front of the windows, right? So actually a common location where we will place brace frames in buildings is either around the stairwells or around the elevator shafts. Because the elevator shafts, you don't really need a window, right? Usually you don't. Like if you go to Smith Hall, right? Who cares if behind the elevator shaft there was a brace? You know, you couldn't see out there anyways, right? So that's a good place to put one. So brace frames are the most common, and then there's also moment frames. So if brace frames are sort of like trusses in CE 312, these are like frames in CE 312. Remember, frames, the difference between a truss and a frame is that a frame can withstand moment. From a design standpoint, moment frames are they're more open. You know, you don't have big braces in the middle of the window. They do tend to be a little bit more expensive, okay? Because you would think this would be more expensive because you've got these big old members, but what makes moment frames more expensive are the connections. You have these really complicated connections and you have to use a lot of them. So they tend to rack up price pretty quickly. You can also use shear walls. Shear walls are also an option. Literally just fill in between a beam and a column, fill it in either with concrete or a steel plate. Not as common as brace frames or moment frames, but again, an option. I just wanted to put a bunch of stuff in your head as we start talking about this stuff throughout the semester. Does this all sound fun? Okay. All right. So a couple other housekeeping items, and then I'll let you go. Again, if you haven't gotten the manual, please try and get that acquired. Again, starting week 3, we are going to use it pretty religiously. I'm going to pull up the QR code one more time to collect attendance. No homework today, but I am going to have a homework assignment on Wednesday through Friday. Again, for these first couple weeks, the homework assignments are going to be pretty short. With that, that's all I got, everybody. I will see you all on Wednesday.